Kirchhoff's laws. And let me make this full screen. Okay, so Kirchhoff's laws. Kirchhoffs. And Kirchhoff happens to have like Ohm's law and Watt's law. These are rather absolute. So there happens to be two that I will share with you. One is KCL. And KCL stands for Kirchhoff's current law. And Kirchhoff's current law says the sum of currents entering any node, and this is an absolute, must equal the sum of currents exiting that node. And let's see where this makes sense from our previous discussion. But this is what you want to make sure you get down in your notebook. So KCL is an abbreviation for Kirchhoff's current law. And Kirchhoff's current law states, it says the sum of currents doing what? Entering any node must do what? Equal to the sum of currents doing what? Exiting that same node. Those are the important highlights from that particular sentence. And if you recall from our circuit analysis last week, and I'll go to our circuit in a moment. As soon as you finish copying this, Kirchhoff's current law states that the sum of currents entering any node must equal the sum of currents exiting that node. Okay, you'll see this definition again, but what I want to just out to is in our schematic last week, what it is that you recall in this intermediate redraw. The intermediate redraw had current, a total current that came from this final redraw. The final redraw, as we did 4 draws here, the final redraw allowed us a single voltage source, an RT, and we calculated an IT. That IT is the current that leaves the source, the same current that enters the source. That IT value of 13.35 milliamps was brought upstairs to this schematic, which instead of just a single RT, we had 2 original resistors, R4 and R5, plus an equivalent resistance over here. That 13.35 milliamps flows through each of those series components and clearly is the current through R4 and is also clearly the current through R5. We take that information back up one more step. And as we're now here, we can see that 13.35 milliamps is going to come into node A. And as it comes into this redraw in node A, the current splits. The current comes out this way to the left through REQ1, comes down straight down through R3, one of the original resistors. So do I have a node? Do I have currents coming in? Do I have currents coming out? And according to Kirchhoff's current law, Kirchhoff says the sum of the currents coming in have to equal the sum of the currents coming out. But there's only one current coming in, 1335. Does this in fact equal the sum of the 2 currents coming out? Well, we were able to calculate last week that the current in this path was 4.47 milliamps, and the current through this path was 8.88 milliamps. And if we go to add those guys up, yes, they do add up to the 13.35 milliamps that came in. Also, if we look at node B, do I have currents coming into node B? I have the current of 8.8 milliamps coming down through R3, and I have 4.47 milliamps coming from REQ1. Do these currents sum to equal the current coming out of node B? And the answer to this is also yes. So Kirchhoff's current law is proved here. A more interesting exercise for us to play with, to expand upon your understanding of Kirchhoff's current law, is if I do this with you. Let's go ahead and put a node here. Let's go ahead and put a node. I'm going to draw 1, 2, 3, 4, 5, 6 paths. And in these 6 paths, I'm going to state, okay, we're going to have 4 amps going this way. I'm going to have 2 amps going this way. I'm going to have 6 amps going this way. I'm going to have 12 amps coming this way. I'm going to have 17 amps coming this way. So the question has to do with this remaining wire out here. What is the current on that particular wire? So on this wire, we have 4 amps going in. On this wire, we have 2 amps coming out. On this wire, we have 6 amps coming in. On this wire, we have 12 amps coming out. And on this one, we've got 17 going in. So how do you reconcile something like this based on this definition? The solution to this, anybody got any ideas?
Would it be 13, the remainder?
Would it be 13, the remainder? What remainder? How are you getting a remainder?
Well, let me see. You got 4 coming in and 6. That's 10. Plus 17. That's 27. And then you got coming out 14. You got 14 coming out.
Yeah.
So that leaves 13 that have to come out because whatever comes in.
Well, that's really, really good. Yeah, Christian, you're absolutely correct. And to help our classmates out and see how it is you deduce that, let me offer this solution method here. You're going to create a simple in and out chart. In and out chart. And so you're going to state all of the currents that are going in. So if we start where we were, we happen to have 4 amps going in here. This next one, we have 2 amps coming out. So let's go 2 amps coming out. This next one over here, we got 6 amps going what? Going in. So you write down 6 amps going in. And this next one, we have 12 amps coming out. So you got 12 amps coming out. And this last branch over here that shows anything shows 17 amps in which direction? Going in. So you have 17 amps going in, and we don't know what is happening with which branch where. We know we have to add these guys up. So if we go to add these guys, let's confirm. Inward, we have 4 amps. Outwards, we have 2 amps. Inwards, we have 6 amps. Outwards, we have 12 amps. Inwards, we have 17 amps. So do we have all of the inbound amps in the in column? And do we have all of the outbound amps in the out column? And according to Kirchhoff, this total here must equal to this total here, because the sum of currents coming in have to equal the sum of the currents coming out. So if we go to add this up, we end up with 27 amps here, yes? If we go to add this guy up, we end up with 14 amps on the side. I want to smudge that, so I'm going to do it this way. So we end up with 14 amps on this side. So clearly there is something that is missing on this side that has to be added in here in order to get us to 27 amps, because we have to have 27 amps coming in to equal to 27 amps coming out. So what is the missing amount that is here? And so the missing amount, as Christian deduced already, if it tallies 27 amps coming in, and it must equal 27 amps coming out, but we've only accounted for 14 amps coming out, how do I find this missing current? what you do is you take 27 minus 14. When you take 27 minus 14, what is the missing current? The missing current works out to be 13, yes? 13 amps. Because when we add 14 plus 13, do we not get 27 amps? Yes. So the answer for this mystery wire here has got to be what? 13 amps. And which direction is it going? Is it going in or is it going out? Well, what column is it in? It is in the outbound. So it will be 13 amps coming out. Are we good with this concept so far? So the method of doing this is very simply set up an in and out chart, mark down all of your inbound currents in the in column, mark down all of your outbound current in the out column, tally them up. Is one side equal to the other side? If one side is not equal to the other side, there is a missing current. What is that missing current and which column is it in? Well, we determined that of these two values, 27 amps was the higher value. That must be the total, the final total of what goes in is equal to what comes out. You confirm 27 amps on this side, but you don't have 27 amps on the outbound side. Something must be missing. How do we determine what's missing? 27 minus what you have noted so far, 14, gives you your 13. I'll give you another one to think about. Let's do this one here. Suppose I happen to have a node, and here, 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 and here. Okay, make this a rather large node. A lot of it's coming together here. And let us say for a moment we happen to have 2 amps, 6 amps, 3 amps, 10 amps, 14 amps, 20 amps, that's a 20, sorry, 20, and then 17 amps, and this one will be our mystery. Now I have to mark down directions for you. So when I mark down directions, let's give you this. Suppose this one goes in, this one goes in, this one comes out, this one comes out, this one goes in, this one comes out, and this one goes in. What to do? Set up your in and out column chart. So you have in currents and you have out currents. And as you look at in and out currents, let's start marking these guys where we started. We started with a 2 amp. So 2 amp was going in. So we have 2A. We have 6 amps. 6 amps is going in. So we have 6A. We have 3 amps. 3 amps is pointing out. So you have 3A here. Over here, you have 10 amps. This is pointing out. So you have 10 amps over here. Then you have 14 going in. So 14 going in. And you have 20 coming out. 20 amps coming out. You got 17 going in. Okay, got a fair amount of numbers here. Let's be sure we do any tallying. Let's just confirm the values and the currents in the appropriate directions. So, oops, here's another one. Let me go ahead and allow. Here we are. Rolando, could you turn off your microphone?
Yeah.
Thank you. Because what's happening is, if all of you could turn off your microphones unless you are ready to do a response, what happens is when any of your microphones picks up any sound, your screen comes on overrides other people's, and we won't be able to see the lesson very clearly. But you all need to turn on your cameras too so I can see your smiling faces. Okay. All right. So welcome, Wenbin. I'm glad you were able to make it. We started to talk about this new lesson. This new lesson is on Kirchhoff's laws. This first is on KCL, Kirchhoff's current law. And Kirchhoff's current law says the sum of currents entering any node must equal the sum of currents exiting that node. And I happen to have an example here, a node, and I've got lots of wires attached to this. And so based on this most recent drawing, I've got 2 amps coming in, that's confirmed, 6 amps coming in, that's confirmed, 3 amps going out, that's confirmed, 10 amps in the outbound direction, that's also confirmed, 14 amps going in, that's in the correct column, 20 amps coming out in the outbound column, 17 amps going in, this is in the inbound column. So each one of these 7 is accounted for as being in the appropriate column. Now let's go ahead and do the tally. So this tally works out to be 39 amps? How many people agree?
39.
39. Yeah. Agree this side is equal to 39 amps. Now let's see what the other side tallies to be. The other side tallies to be 33 amps, yeah? All right, so we have 33 amps. So right now, do we have equality?
No.
We do not have equality. That means something must be added to this column in order for us to get to 39 amps out to match the 39 amps in. They have to equal each other according to Kirchhoff's law.
So that other one's 6 amps.
Yeah, all inbound currents have to match up with the outbound currents. And so as you can deduce, 39 minus 33, the difference is 6. 6 goes right here. And our missing current is 6 amps in which column? In this case, the out one. So this one is equal to 6 amps and moving with an arrow showing it's coming out. Are we okay with our understanding of Kirchhoff's current law based on these 2 examples? And what we'll do is, as I've done before, I'll take our entire recorded lesson in Zoom. You'll have the entire lesson as one complete session in a recording in Canvas, not in Canvas, but in YouTube. And what I'll do is I'll chunk it out into different parts so that you will see Kirchhoff's current law as one component and Kirchhoff's current law as another component, and we'll go from there. So in more complex circuits, as long as you remember using Kirchhoff's current law, you hopefully can easily reconcile your current analysis by using the in and out chart like this in order to find the value of the missing current. Any questions about Kirchhoff's current law bar? Okay, next to Kirchhoff's current law will be over here. Kirchhoff's voltage law. And this is KVL. So you have a KCL and you have a KVL. KVL can be described one of 2 ways. One definition is this. The algebraic sum of all voltages in any closed loop must add to 0 volts. The algebraic sum of all voltages in any closed loop must add to 0 volts. And so what I'll do is I'll go ahead from last time, draw out for us the circuit for our 5 resistor series parallel analysis, specifically with voltage drops that we were able to determine from last time. So what I mean to say here is we had a resistor and it came to a node A, and we had another resistor and it came to a node B. We had another resistor. This was our R3. We had another resistor over here. And we had another resistor over here. And we had this, and this, like so. We had an R4 in this location. We had an R5 in this location. We had an R1 over here. We had an R2 over here. The voltage source was given as 28 volts. The polarities that we would mark on this particular guy would always be determined by our voltage source. Our voltage source has what plate on the top? Negative, positive on the bottom. So go ahead and think about this for a moment and see if you can polarize, see if you can correctly polarize the resistors in this particular circuit. Which lead, left, right, top, bottom, left, right. Which lead is going to be positive, which lead is going to be negative. Now, a couple things that'll help you out were our drawings from last time. The drawings from last time, I'll put it back on this in front of the camera here. If you take a look at the most simple drawing, does it in fact show the negative plate on top, the positive plate on the bottom? Does it show electron current leaving the negative plate going through the circuit, and which way, what do you call this direction of current flow? Is this going to be clockwise or is it going to be counterclockwise?
Counterclockwise.
This is going to be counterclockwise. If you don't recall what I'm talking about, boom, here's a clock. Which way is the second hand moving? The second hand is moving clockwise. So if the current is moving in the opposite direction, that is called counterclockwise. So that being said, the current in this case leaves the source in a counterclockwise fashion through the schematic. If we take this information through here, we can also verify this current is going counterclockwise, flowing in this direction through the 3 resistors. That became our total. If we take this current back upstairs to here, we can see that the current still flows up and to the left, and it hits this node. If it hits this node, it then splits. We said part of the current comes down through R3, part of the current continues over through REQ1. At the bottom of the circuit at node B, the current comes from the left to the right into node B, and it comes from the top to the bottom into node B. They combine and give us back to the current source. That's how currents flow in this particular schematic. Now, this is described as electron current flow. So perhaps what will be helpful to us here is if we reiterate electron current flow. So just as a reminder, and I'll put this up as a reminder, here, reminder, this is electron flow model. Because there happens to be 2 different models of current. Electron flow model is one of those models. And electron flow model, number 1, current leaves negative side of Vs. So it leaves, which I'm abbreviating negative. So the current leaves the negative side of the voltage source and returns to positive side. Okay, so it returns to the positive side. The second consideration is this. Current flows from negative side of devices through them to the positive side of those devices. So that's a good reminder. We mentioned this way back in week 1 and 2 of our semester about electron current flow model, because the alternative to electron current flow model has a name. Who remembers the alternative current model? Anybody?
Conventional?
Very good, Christian. It is conventional current flow. And conventional current flow is completely opposite of all of this. Instead of, for conventional current will leave the positive side of the source and return to the negative side. And conventional current flows from the positive side of the device through them to the negative side of the device. So there are two different models of current flow. We'll just stay with the electron current flow. I said that from week 2, that this was the easier model to understand for beginners. And we do use the other current model when we get into the more advanced electronic classes. So that being said, the key word here is current flows from the negative side of these devices through them to the positive side of these devices. So that being said, take a look at, well, let's go ahead and take a look at this circuit here. Can we go ahead and start drawing our arrows for current flow and then also fill in the polarities? We said in the previous circuit that current that flowed from the negative source up and over to the left. It will flow through R4. And as it flows through R4, it will flow from the right to the left, from the right to the left. So it'll flow in this fashion, yes? So as it flows in this fashion, what polarity must be on the right side based on definition number 2 of electron flow model?
Negative.
Yes, this side must be negative. So we will have negative over here. This side must be negative because it must flow from the negative side of the device. Then what's it say? Through them, and it ends up where? To the what?
Positive.
Positive side. So that means this side, it flowed through the component. That means on this side, this component must be what polarity on the left-hand side? This side must be positive.
Positive.
Right there, okay? Are we good with the polarity based on the electron current flow? So far, so good?
Mm-hmm.
Then the current comes along and it hits this node and it splits. And we say part of the current comes down and part of the current continues on through the left. Well, let's analyze what happens with the current that comes down. The current that comes down through R3 is from the top to the bottom. So it enters the top, comes out of the bottom. Enters what side of the device? What's my definition say? Negative side of the device, and it ends up, so negative side on top and positive side on the bottom. So far, so good. And let's take a look at what happens through R2. Through R2, the current goes through R2 from the right side to the left side. So it's just like what happens with R4. The current flowed through R4 from the right side to the left side. So this side that it flows, where it flows into the device, must be what polarity? This side must be negative.
Negative.
This side must be positive over here. And then we'll go ahead and continue marking. These currents come down through R1, and by the same token, as they come down through R1, they came down through R3. This side must be negative, this side must be positive, like so. And then the current will continue here, here. Is there any polarity on that wire? Is one side of the wire positive, one side of the wire negative? No,
No.
it's just a wire. Okay, so that answer is a no. It's just a wire. It's not a device. Then the current combines at node B, and it leaves node B and goes back to the source in this direction, like so. So as the current flows into R5, it flows into R5 from the left through it to the right. So it's got to go into what side of the device? It's got to go into the negative side of the device.
Negative. Negative.
Coming out of the positive side of the device right there. So that's how you determine how to mark your polarities of any component on here, is by understanding Kirchhoff's current law, by understanding how currents leave the source, by understanding the reminder of the electron flow model, that electron current always leaves which side of the source? The negative side of the source, and always returns to what side of the source? The positive. And is that what we have here? We have it leaving the negative side, flowing through the circuit, and then coming back to the positive side. That's part one of the definition of electron current flow model. The second definition of electron current flow model is it establishes the polarity of the devices that the current flows through. And the electron current will always flow from the negative side of the device through the device to the positive side. So as it flows through R4, it's got to flow from the negative to the positive. As it flows through R2, from the negative to the positive. As it flows through R1 and R from the top to the top of these will be negative, the bottom of these will be positive. And as it flows through R5 from the left to the right, it's got to be negative on this side, positive on this side. So far, so good? Okay, okay. Now, we still haven't, we've got most of the elements in place that will allow us to start looking at Kirchhoff's voltage law. And on Kirchhoff's voltage law, algebraic sum of all voltages in any closed loop must add to 0 volts. Well, let's go ahead and put in some voltages now. The voltages that we were able to determine last time were here. These were the voltages that we determined from this circuit analysis last time. So I'm going to set this guy aside. I'm going to write down the values that we have. The voltage across R1 was deemed to be 4.38 volts. The voltage across R2 was deemed to be 8.94 volts. The voltage across R3 was deemed to be 13.32 volts. The voltage across R4 was calculated to be 4.40 volts. And the voltage across R5 was 10.28 volts. Okay, so we just transfer all of the calculated voltages over to here. And as we go to add things up, keep in mind, depending upon how you're using your calculator, how we rounded off or did not round off, we could be hundredths of a decimal place apart. But let's see what happens. All right, so let's go ahead and take a look at a loop. If I take a look at this particular loop right here, okay, and I'm going to start at point A, and I'm going to go around in this fashion, in a counterclockwise fashion. So I'm going to say loop number 1. I know that color is a little hard to see, so I'll just do it here. Loop number 1. So as I analyze loop number 1, if I start at point A and I move in a counterclockwise direction and I come back to point A, let's see what kind of values we end up with. If we start at point A and we move to the left in a counterclockwise fashion, what's the very first polarity and value that we encounter? We see a what? Negative, and we see an 8.94 volts, yes? So you have negative 8.94 volts. We're going to add that to, now we're on this point, now we're going to go from here down, and as we are on this point, what's the first polarity we see? See a negative, and what value do we see? Negative 4.38 volts. So we're going to add that to a negative 4.38 volts. Now we're on the bottom side of R1. Is there anything on that wire between this corner and point B? Nothing. Now we're at point B. While we're at point B and we bring our analysis back up to point A, what do we encounter? We encounter a positive what? So we're going to add that to a positive 13.32 volts. Add that up algebraically. Do I end up with 0 volts? Is that a thing of beauty or what? Is Kirchhoff rolling over in his grave, or is he smiling down on us? He'd be happy camper, okay? Because that loop worked out to be 0 volts. Now let's go ahead and analyze what happens over here in a second loop. Loop number 2. And in loop number 2, we're going to look at this loop, and I'm going to go here like so. And then this particular loop, let's see what happens. I'm going to start at node A and go down to B, go to this corner, come to this corner, and come to here. Okay, so that's my analysis. So watch me again. I'm going to start at A. I'm going to come down to node B. I'm going to go to this corner, back to node A. So let's see what we encounter in terms of the values here. So numerically, the very first thing we see from A to B is going to be what polarity? Negative and negative 13.32 volts, right? So I have negative 13.32 volts. And I'm going to add that to, now I'm at point B, I'm going to the right. At point B, going to the right, first polarity I encounter is going to be negative what? 10.28 volts. So add that to a negative 10.28 volts. Now I'm at this corner. At this corner, what do I see? Oh, I see a positive how much? So I'm going to add a positive 28 volts. And now I'm at this corner. So at this corner, what do I encounter? At this corner, I encounter, a negative, and this is a negative 4.40 volts. So I'm going to add that to a negative 4.40 volts. And let's add these guys up and see what it is this will tally to. So as I said, we could be within 1/100th of a decimal place off because we rounded earlier, but we have a change sign 13.32. I'm going to add this to a change sign 10.28. I'm going to add this to 28. And then I'm going to add this to a change sign 4.4. And if I go to tally this, I end up with, wow, 0 volts. Is Kirchhoff a happy camper so far? Kirchhoff's a very happy camper so far. We have one more loop. Who can tell me what my one more loop is?
The entire box?
The outside, right here, yes. So we did this left side, we did this right side, but we could also have big loop on the outside. So we have one more loop, loop number 3. And on loop number 3, again, I'll start at point A since it's a designated point, and I will go in a counterclockwise fashion until I come back to point A, which means I'm not going to count the value of R3, right? Because that's not part of the outside loop. So again, the outside loop is from A to this corner, down to this corner, to point B, to this corner, through the 28 volt to this corner back to A. So let's see what we have to add up. So starting at point A, moving to the left, I encounter a negative 8.94. So negative 8.94 volts. And I'm going to add that to, and then I encounter a negative 4.38. So I write down negative 4.38 volts. Then I have nothing on this wire. Then I'm at node B. Now, where should I go when I'm at node B? Do I count this voltage here going up? No, that's not part of my outside loop. I continue going on the outside until I encounter this resistor. What do I see on this resistor is a negative what? 10.28. So I'm going to add negative 10.28 volts. Now I'm at this lower right-hand corner. At this lower right-hand corner, I encounter a positive 28 volt source. So I'm going to add 28 volts. And then I'm at this corner, one more resistor to go. And with one more resistor to go, I have a negative 4.40. So I'm going to add this to a negative 4.40 volts. And now I'm back at point A. So now let's see mathematically how all this works out. So change sign, negative 8.94, add that to change sign, 4.38, add that to change sign, 10.28, add that to a regular 28, add that to a negative 4.40, and then hit enter. Oops, I messed up somewhere. Somewhere I didn't have. Somewhere, okay, I'll do this again. Pardon me, negative 8.94 plus negative 4.38 plus negative 10.28 plus 28 plus negative 4.4, end up with, wow, how about that? 0 volts. So that's pretty exciting. I know you're all just clapping your hands and patting yourselves on the back and saying, wow, that's amazing. Well, Mr. Kirchhoff, way back when, figured out his current law, and he also figured out his voltage law. The algebraic sum of voltages in any closed loop absolutely, positively must add to how many volts? 0 volts, okay? I wrote down the definition 1. There is also a definition 2, but definition 1 is really the best one, and at some point in time, I'll talk about definition 2. Fundamentally, in more basic circuits, that the algebraic sum of voltages in a closed loop must add up the voltage source. So if I have a closed loop here, these voltages algebraically must add up to this voltage source. And they happen to. So in this closed loop, we demonstrated that earlier because this one portion of the circuit has a closed loop, has a voltage source in it. And if I add this plus this plus this, as we did in loop number 2, it added up to be the voltage source. This could also be said here is the outer loop, loop 3, includes the voltage source. So Kirchhoff's law says in any closed loop, the algebraic sum of voltage drops must add up to the voltage source, and they do in here as well. I like this definition because this applies to everything where I don't have a voltage source. So the algebraic sum of voltages is any closed loop must add to 0. Boom. That adds to 0. This adds to 0. And the outer loop adds to 0. So you'll see 2 stated definitions of Kirchhoff's voltage law in the literature. This is the one that I find is has the most universal application. Any questions about Kirchhoff's laws, Kirchhoff's current law and Kirchhoff's voltage law, and a reminder of how electron current flow helps you determine the polarity of components in a circuit. So far, so good?